we're going to discuss how, from starting from equilibrium principle, Einstein got the idea of a geometric theory of gravity, which is GR. uh, it's by considering the physics implied by equilibrium principle, Einstein got the idea that the gravitational field can be modeled as a curved space-time. In this effort, Einstein was helped by his friend, the mathematician Marcel Grossmann. Grossmann was Einstein's college classmate, and uh, there were stories saying that Einstein skipped a lot of lectures, so he relies on Grossmann's meticulous notes to pass the exams. Uh, After college, Einstein had a very difficult time finding an academic job, and eventually it was Grossmann, through his father, who was able to help Einstein get a job in the patent office. And then Einstein did all his famous work in 1905 and later on, and finally got academic jobs, moved around a bit. For example, he spent a year and a half in Prague, in Czech Republic, and then he went back to join the faculty of the University of Zurich in Switzerland, and there Grossman is also a faculty member, so they become colleagues again. It's that time that Grossman introduced Einstein to the work of Bernhard Riemann and Christoffel and others, namely uh, the Riemannian geometry, which of course is the language of GR. So Grossman really has been was a very important person in Einstein's life. So uh, we're talking about GR as the geometric theory of gravity. So what is a geometric theory? What do we mean by a geometric theory of physics? Such a theory attributes the result of physical measurements directly to the underlying geometry of space and time. Okay, that's what we mean by a geometric theory. Give an example. For example, talk about length measurement on a globe, and you have longitudinal distance and latitudinal distance. And from the east-west distance between two points that's sustained by the same azimuth angle, the latitudinal distance, which is getting smaller and smaller as we approach to the pole, while the longitudinal distance held by a fixed polar angle interval remain the same from pole to equator. Now, without taking the fact that the two-dimensional space is curved, we could have thought that the dynamics, the physics dynamics, such that the measuring rod changes scale at different locations when it point out in the different direction, longitudinal direction, or towards the pole. Much like the Lorentz length contraction in special relativity was originally interpreted by Lorentz as due to some sort of dynamic forces causing the object to contract in the direction of motion. But alternative, we can use the same standard ruler with the fixed scale and attribute the various length measurements due to underlying the geometry of the, in this case, curved surface. This obviously is a much more efficient and way to dealing with it. And for curved surface means that the non-trivial geometry is expressed mathematically by a position-dependent metric tensor. It's no longer flat, no longer a constant. So let me say it again, how going from equivalent principle to GR, the equivalent principle is the empirical principle that find equivalence between gravity and inertia. And the geometric theory is that to attribute the gravitational phenomena as due to the underlying curved space and time. Now the geometry is described the metric which relates the length measurements to the chosen coordinates, the Gaussian coordinates. Now in special relativity, the we have a flat uh, space and time, so therefore we can have a position independent metric like eta mu nu, which is diagonal minus 1, 1, 1, 1. But the study of equivalent principle physics led Einstein to propose that gravity represents the structure of curved space-time. And it was in the absence of gravity, space-time is flat. In the present gravity, the space-time is curved, and its metric no longer is constant. So the gravitational phenomena is simply the effect of curved space-time on a test object. Now, let's talk about a particular example, a concrete example, talk about how a gravitational time dilation can be viewed as bending, as due to bending of space-time in the time direction. So instead of working with complicated scheme clock running at different rates, the gravitational time dilation can be interpreted geometrically as showing a non-trivial metric. Okay. Remember, we talked how the elements of metric can directly relate to length measurements, length measure ds, and in terms of the chosen coordinates. So g00 ds, which is the length measurement in the zeros direction, and dx naught is the time coordinates. Dx naught is the t is the coordinate time, which is measured by clock located far from the source of gravity. And the lengths in the zero direction, which means that dx dy dz equals 0, so it's a stationary clock, and so therefore this is a proper time. So therefore the length measurements in the zero direction is minus c t tau square. Now if we replace the x naught by ct here, replace s naught by the proper time, then this relation can be expressed as the proper time interval square equal to minus g00 times the coordinate time squared. But we remember we have this equivalent principle of gravitational time dilation result, which relates the proper time to the coordinate time in this through the gravitational potential. So if we square this, we compare this to expression, we'll find that g00 simply is minus square of this parentheses, which because phi over c squared is a very tiny quantity, we can approximate by this minus 1 plus 2 phi over c squared. Interpretation of gravitational time dilation is that gravity is warped space-time. In this case, in the time direction means g00 different from minus 1, change space from minus 1 to an x-dependent function like this. Okay, so that's the geometric interpretation of gravitational time dilation. So we're going to see further argument for that. We can interpret gravitational field as curved space-time, or we can model the gravitational field as a curved space-time. And as we just said, we can interpret the equivalent principle of physics like time dilation as showing warp space-time. Now, we certainly have, this suggests a metric, a position-dependent metric. And since the metric tensor for a curved space is necessarily position-dependent, so this is certainly compatible with the fact that we can model the curved space-time as a gravitational field. In fact, in Einstein theory, the metric function, the g mu nu, completely describes the gravitational field. So really we can view this g mu nu as a relativity of gravitational potential. Okay. Just like phi is the Newtonian gravitational potential. But you notice in Newtonian theory, the gravitational potential is only one component. And in relativity, the gravitational potential is symmetric 4x4 matrix, so have 10 independent components. And also, we say it's modeled by warp space-time, which means that we expect in the presence of gravity, so space-time warped, that we have non-Euclidean relations. Okay. For example, let's consider a concrete example. Let's say we have a rotating cylinder. So it's rotating fast this way. So therefore, there's radial direction. You have centripetal acceleration. By equivalent principle, you can view that as you have a cylindrical symmetric gravitational field. But now, because it's rotation, you have length contraction in the direction of circumference, but because in the radial direction is perpendicular to the direction of motion, there's no length contraction. So therefore, the relation between circumference and radius no longer 2 pi r. So therefore, the Euclidean relation is no longer holds in the presence of gravity. Now we have to make a very important point. That's in a curved space, it's locally flat. Means we can always go to a small enough area to pass by by a flat surface. So this is the Flattened Theorem. Now for a curved space-time, so we'll have a locally flat space-time. No flat space-time is no gravity. This in green was Coulomb principle. In Coulomb principle, that you can always go to a free fall frame locally to in which the gravity is transformed away. Okay. So therefore, GR automatically and precisely incorporates the Coulomb principle through the Flattened theorem. Let me give you another illustration of the geometric theory. Consider two particles, both travel north from the equator. Okay, the geodesic, so they'll follow great circles, and these two geodesic getting closer and closer, so the particle get closer and closer. Now we can explain that either say that there's an attractive force between these two particles. That's the reason why they get closer and closer when travel along. Or we can say that the underlying geometry is a curved spherical surface. Okay. Now this, of course, is a two-dimensional illustration, and GR we're talking about four-dimensional space-time, but the same thing, the curvature in the four-dimensional space-time causing the non-trivial motions of test particles. In fact, we will have a GR equation of geodesic deviation showing that the geodesic would be bent by the present curvature. Now we're going to talk about curved space-time and gravitational redshift. Remember, we use the equivalent principle. We derive the result of gravitational redshift. Frequency changes due to the receiver and emitter located at different gravitational potentials. So difference of frequency related to difference the potential. And of course, we're talking about a static gravitational field. Then through gravitational redshift, we deduce the idea of gravitational time dilation. Okay. From gravitational time dilation, we say we can interpret it as curved by curved space-time, a bending in the time direction, which we talked about 2 slides ago. So in other words, we've gone from gravitational redshift and derived to curved space-time. Now, in some ways, we're going to go in the opposite direction. We can show how curved space-time implies directly the gravitational redshift. Okay. And the curved space-time expressed, for example, the proper time interval is related to the coordinate time interval by this non-trivial metric element G00, which is related to gravitational potential. Now let's consider a space-time diagram of a train train of waves. Okay, and the emitter is here, and the receiver located here. So therefore, their whirl line are straight lines. Okay, because they stay put at the one position, and then these are the whirl lines for the say two peaks of light, and they're sort of wiggly because try to indicate that the space time uh, may be warped due to gravity. But these whirl lines are still congruent, means that uh, the same place goes up, the same time goes down. The reason because we're talking about a static gravitational field, so a static uh, space-time. So therefore, the time interval between the two wave trains is dt, which is same throughout the trip from initial point of dt at the emitting point to the receiving point. The time interval between the two peaks are remain the same. Now we're going to derive the gravitational redshift. So the frequency difference between receiver and emitter, because frequencies are related proportional 1 over the proper time interval. So it's the proper time interval at the emission point divided by the proper time in the receiving point. But the proper time can be expressed in terms of coordinate time through the metric. So we do that for the numerator and denominator. And we just argued that the coordinate time at time interval at the emitting point and at the receiving point are the same. So therefore, these two dt factor cancel, and we're left only with the right-hand side is gravitational potential expression. So this is gravitational redshift. The frequency difference is related to gravitational potential. Now we're going to try to show how this is just, you simplify this factor because phi over c squared is very small, so that can be approximated by times minus 1/2 factor. The two cancel, so minus phi over c squared, and so this is 1 minus phi squared over c squared, and the denominator have the same thing, but then put on the numerator that become plus phi em squared. So therefore, this of course is just the same expression as this. Okay, so therefore, we can derive the redshift result directly from curved space-time. This is the end of second part of lecture 11.